Hi friends, welcome to CS Academy. In this session, I will explain what is the Newton's law of viscosity and classification of fluids. Let's start the session. Newton's law of viscosity states that shear stress which exists between the layers of a fluid is directly proportional to the rate of shear strain. Here, we can indicate this as tau is directly proportional to rate of shear strain. Okay, if we remove this proportionality, we have to introduce one constant, that is viscosity. Tau equal mu into du by dy. Here mu is nothing but of coefficient of viscosity or dynamic viscosity. Okay, here mu is nothing but of coefficient of viscosity or dynamic viscosity. This is the law of viscosity which is derived by Newton's. Okay, so let's discuss the classification of fluids here. Fluids are generally classified into two types, that is real fluids and the second one is ideal fluids. Before going into this classification, first we should know that fluids are incompressible. Everyone know that fluids are incompressible, but they don't know the reason why. Okay, here the compressibility beta equal inversely proportional to the bulk modulus. Here compressibility of a fluid is nothing but of change in pressure to volumetrical strain, that is dP by change in volume by original volume. Here we can also written as VdP by dV. Okay, here dV is nothing but of a change in volume of the any fluid, but the volume don't change for the any fluid, so it can be taken as 0, that is K value something by 0 is nothing but of infinity. Okay, here bulk modulus is infinity for the fluids. If we substitute this value in the compressibility, beta equal to 1 by K, that is 1 by infinity. Okay, 1 by infinity is nothing but of 0, that is compressibility of any fluid is 0, that is nothing but of incompressible. Okay, this is the concept behind why fluids are incompressible. Let's come to the topic. Here classification of fluids, the first one is a real fluid. Real fluids are incompressible and viscous. Here any fluid which is the having property of viscosity, that is viscosity is not equal to 0, that fluid is nothing but of a real fluid. Okay, each and every fluid which is existing in the nature is a real fluid only. Okay, if we see the next one is ideal fluid, any fluid which is having zero viscosity. Okay, which is having zero viscosity, those fluids are ideal fluids. These ideal fluids can be written as incompressible fluids and inviscous fluids. Okay, both incompressible and inviscous fluids are called ideal fluids. In nature there is no any fluid which is having zero viscosity, so that ideal fluids are not available on the nature. Okay, it is just assumption. And if we see the classification of real fluids, these real fluids are again classified into two categories. The first one is Newtonian fluids, the second one is non-Newtonian fluids. Okay, these Newtonian non-Newtonian fluids are real fluids only, these are not ideal fluids. Okay, here what is the meaning of Newtonian fluids means, if any fluid which is obeying Newton's law of viscosity, that is tau is directly proportional to du by dy, then that fluid is called Newtonian fluids. Okay, here listen carefully. Any fluid which is obeying Newton's law of viscosity, that fluids are called Newtonian fluids. If we consider some examples like water, air, gasoline, that is petrol, like this, these are the examples for the Newtonian fluids. Okay, if we see non-Newtonian fluids, any fluid which is not obeying this Newton's law of viscosity, that is tau is not directly proportional to du by dy. That means it is not obeying this Newton's law of viscosity. Then the proportionality is not equal here. Okay, so that those fluids which are not obeying this Newton's law of viscosity called non-Newtonian fluids. Okay, that is for Newtonian fluids tau equal mu into du by dy. Okay, for non-Newtonian fluids, tau is not equal to mu into du by dy. Okay, that means something we should add here to equate this value to the tau value. Okay, so that here mu is constant for the Newtonian fluids. Okay, for these non-Newtonian fluids, what is the mu value? Okay, this is the question here. Most of the students don't know, but they directly think that for Newtonian non-Newtonian fluids, mu is equal. Okay, but it is not correct. Mu is constant for the Newtonian fluids, but mu is not constant for the Newtonian fluids. It will vary based upon the type of the fluid, type of the non-Newtonian fluid. Okay, here for non-Newtonian fluids, we will consider this viscosity as apparent viscosity mu suffix a. Okay, apparent viscosity. Please listen carefully. It is very, very important. Okay, you cannot find in any book, and some foreign authors only they will put this type of information. Okay, this apparent viscosity mu a is nothing but of constant viscosity. That is what we are using in this Newtonian fluids, mu into du by dy whole power of n minus 1. Okay, this is the formula, that is the apparent viscosity for the non-Newtonian fluids. Here you can have doubt that what is the value of n. N is nothing but of flow index. Okay, flow index. It will vary based upon the type of non-Newtonian fluid. Okay, please listen carefully. And the study of non-Newtonian fluids is called rheology. Okay, rheology. And if you see the classification of non-Newtonian fluids again, this is the classification of non-Newtonian fluids, that is pseudo-plastic fluids, dilatant fluids, Bingham plastic fluids, thixotrophic and rheopectic fluids. These are the classification of non-Newtonian fluids. Out of these all fluids, these three are time independent fluids. Okay, these three are time independent fluids. These fluids don't depend on the time. It will not consider the time. Okay, here these two fluids are time dependent fluids. That means the viscosity of these two fluids vary with respect to the time, but the viscosity of these fluids will not consider the time. There is no any factor that is affecting the viscosity. Okay, so here if we see for Newtonian fluids, tau equal to mu into du by dy. Okay, for Newtonian fluids. For non-Newtonian fluids, tau equal to mu apparent into du by dy. Okay, here this is for non-Newtonian fluids. Here we know mu apparent is nothing but of mu into du by dy whole power of n minus 1 into du by dy. This plus 1, this minus 1 get cancelled. That is called tau equal to mu into du by dy whole power of n for what? Non-Newtonian fluids. If n, that is flow index, equal to 1, what will happen? This will become tau equal mu into du by dy, that is nothing but of Newtonian fluids. That means that flow index is not equal to 1 for non-Newtonian fluids. That is, it may be greater than 1, less than 1. Yes or no? So here this is the equation for non-Newtonian fluids, very, very important. And if we draw graph for this time independent and time dependent fluids, that is, let us consider this is horizontal and vertical axis like this. Okay, on this vertical axis we are taking a shear stress, on this horizontal axis we are taking this rate of shear strain du by dy. Okay, for Newtonian fluids, tau equal to mu into du by dy. Let us consider this is as y equal to mx. Okay, this is vertical axis, this is horizontal axis, this is the slope of any curve or any line which is drawn on this graph. Okay, here if you see mu equal to tau by du by dy. Okay, as like m equal to y by x. Okay, similar to this one, tau mu equal to tau by du by dy. If I draw graph for the Newtonian fluids, here for Newtonian fluids flow index n equal 1. That is, mu value what? Is a constant value. If we take tau value 10, if we take du by dy 20, that is 1 by 2. If I consider 1 by 2 here, if I draw like this, if I go on increasing the values, even though increasing the tau value and du by dy value, but the ratio between this tau and du by dy equal to 1 by 2 only, that is constant. For that slope is constant means we will draw graph as like a line which is passing through the origin. Okay, this is for Newtonian fluids. Listen carefully here. Why we are drawing this line as this straight line from this origin means here mu is nothing but of tau by du by dy. Here mu is constant for this what Newtonian fluids. Here we are comparing this equation with the y is equal to mx. Here m is nothing but of slope. The value of this ratio y by x is constant for this Newtonian fluids. Constant in the sense that if you take ratio, it is equal everywhere. Okay, it is equal everywhere. Okay, here this is Newtonian fluids. If we consider non-Newtonian fluids, that is a pseudoplastic. For pseudoplastic, the value of the graph will be like this. Pseudoplastic. Okay, this is for pseudoplastic. And for dilatant fluids, the graph will be like this. Okay, for dilatant fluids. Okay, and one more thing, Bingham plastic, it is also comes under time independent fluid. Okay, these are time independent fluids. And one more thing, that is Bingham plastic. For Bingham plastic, the value of the shear stress tau, actually for non-Newtonian fluids, tau equal to mu apparent into du by dy. Am I right? For this Bingham plastic, there should be, to equate these two, there should we add some yield stresses, that is yield shear stresses tau y plus mu apparent into du by dy. Okay, this is equation for this Bingham plastic. Okay, to represent this yield stress, we should go from origin to some value. Okay, this is nothing but of yield stress. Okay, from this point here we should draw as like parallel to this one, this Newtonian fluids, but we should bend somewhat inclination to the downward like this. Okay, here we should draw somewhat bend like this. Okay, some inclination. This is for Bingham plastic curve on the tau 1 du by dy axis. But here if we see for solids or for liquids, okay, here if you see for ideal fluid, viscosity equal to 0, that is mu equal tau by du by dy. This ratio is 0 means that the numerator is 0, that is shear stress is 0. Shear stress is 0 on which axis? Horizontal axis. On the horizontal axis we will take this ideal fluid. Okay, ideal fluid. If we consider this vertical axis, on this vertical axis x axis is 0, that means the value of x is 0, that means du by dy, this is the rate of deformation. The rate of deformation is 0, then we will consider that any body on this y axis. Here du by dy is equal to 0 for the solids. Okay, so that we will consider this y axis as for solids. Okay, on this x axis we are considering ideal fluid because the shear stress, that viscosity is 0. Due to that viscosity is 0, the shear stress is also 0. So that we are considering this ideal fluids on the x axis, and du by dy equal to 0 for the solids. So that we are considering this solid on this y axis. Okay. Here I told you that for non-Newtonian fluids, tau equal to mu apparent into du by dy. Am I right? Here for non-Newtonian fluids, viscosity is not constant. That is, viscosity will vary based upon the type of fluid, like dilatant fluid, pseudoplastic fluids, like that. Okay, but here you will get doubt that which fluid will get increasing the shear stress, viscosity, and for which fluids the viscosity will decreasing. Here I will explain with the help of this graph like this. For example, if we consider the dilatant fluid which is non-Newtonian fluid, the graph will be like this. Yes or no? Here if we consider this mu A, here apparent viscosity, here I am considering 2 points like this. Okay, if I draw one tangent to this curve, the tangent will pass through this point like this, okay, like this on this point. If we consider these points, the angle of these lines which are drawing on these points, the theta values, those are go on theta 3 greater than theta 2 greater than theta 1, like this. These angles are going increasing, yes or no? As we know that theta is nothing but a slope of any line, yes or no? As the slope is increasing, the value, that is the shear stress, the viscosity will go on increasing. For dilatant fluids, mu apparent is go on increasing, yes or no? So that the value of flow index n is greater than 1 for this dilatant fluids. Please remember this one important. N is greater than 1 for the dilatant fluids. I explained this. Why this n value is greater than 1 means, here the slope of this tangents which are drawn on this dilatant fluid curve is go on increasing, so that the value of n is greater than 1. If I consider this pseudoplastic graph, this will be like this, okay. If I draw tangent on this line like this, yes or no, like this, like this, these lines which are going on flatting, yes or no? Flatting means here if we go at some point, the line will be horizontal. Here in this graph, if we go on increasing, the line will be vertical. The tangent line will be vertical. For vertical line, theta is greater than, theta equal to 90, yes or no, for vertical line. Here for a horizontal line, theta is equal to 0. As we are moving from this point to this point, okay, as we are drawing the tangents, the theta value is going decreasing and finally it becomes 0, yes or no, for pseudoplastic. For pseudoplastic, theta is going to decrease from this initial point to the final point, so that the value of flow index n is less than for the pseudoplastic fluids, okay. For Newtonian fluids, you already know n equal to 1, yes or no. For Bingham plastic, the line is like this, yes or no. For Bingham plastic, tau equal to tau y plus mu apparent du by dy. Here also there is no n value, n equal to 1, yes or no. This is how this flow index values, that is n value, is depends upon the type of the fluid. Here n is greater than 1 means that is a dilatant fluid. Because of this greater than 1, the viscosity, that is a mu value, is going to increase, so that dilatant fluids are called shear thickening fluids, okay, shear thickening fluids, because of n is greater than 1. Here for pseudoplastic fluids, n is less than 1, that is a viscosity is going to, apparent viscosity is going to decrease, so that these fluids are called shear thinning, okay. This is thinning, it is thickening, okay. As like we can consider example of this one, like any oil which is low viscous. Here for this one castor oil, like this thickening, okay. If we pour on the floor, it will not flow easily because of this thickening fluids, okay. This is the analysis of this non-Newtonian fluids on this based upon the graph, okay. Here some of the examples are there for dilatant fluids like butter, sugar solution, like this. For pseudoplastic fluids, blood, milk, rubber, paper pulp, like are there. For Bingham plastic fluids, the examples are toothpaste, sewage sludge and drilling mud, okay. Till now we discussed the time independent fluids, yes or no. Now we will consider this time dependent fluids. Those are the thixotrophic and rheopectic fluids. We should draw the graph for this time dependent fluids like this. On the horizontal axis we should take time, because these fluids are depending on the time. On the vertical axis we have to take this apparent viscosity, okay. Here these fluids will vary, this viscosity will vary with respect to the time, so that these fluids are called time dependent fluids, okay. If we draw graph for rheopectic fluids, the apparent viscosity will go on increasing with respect to the time, okay. This is for rheopectic fluids. And for thixotrophic fluids, the graph will be like this. That is, as the time is go on increasing, this apparent value will going in decrease. This is thixotropic. This is the graph for this time dependent fluids, okay, time dependent fluids. Remember this one, and don't draw these two fluids on this tau and du by dy graph. Okay, and here let us consider one example which is asked in IES exam. Let us consider apparent viscosity is, for example, 0.007 into du by dy whole power of, for example, 0.3. Let us consider this is the given in the exam. He is asking that what is the type of fluid. Okay, he is asking what is the type of fluid, whether it is a dilatant fluid or pseudoplastic fluid or Newtonian fluid, non-Newtonian fluid, whatever he is asking that. Here first we have to consider that he given apparent viscosity, that means it is a non-Newtonian fluid. Okay, non-Newtonian fluid. There is no any doubt that it is a Newtonian fluid. Directly we can consider, because of he given this apparent viscosity, we should consider this is a non-Newtonian fluid. Here everyone will think that this is the n value, n equal to 0.3, that is less than 1. We will directly prove that pseudoplastic fluids as an option A. He will give options like pseudoplastic, B dilatant, C Bingham plastic, D none of the above. Everyone will think that this is the value of n is less than 1, so that we will directly select this option A. We don't see whether the other options are not are there. Yes or no? But this is not correct. Why? This apparent viscosity mu A equal mu into du by dy whole power of n minus 1. Okay, and equate these two equations, n minus 1 equal to 0.3, whatever he given in the question, and n equal to 1.3. Yes or no? So here n equal to greater than 1. Okay, n equal greater than 1. This greater than 1 means is nothing but of dilatant fluids in the non-Newtonian. Yes or no? So we should select the option B, which is a dilatant fluid. This is one of the best example to understand the type of fluids. Okay, this is the total about the classification of the fluids and Newton's law of viscosity. I think you got the point. I think you got a best explanation from my video, and thank you for watching, and please subscribe for more videos, like and share. Thank you. And one thing, this total explanation what I did here, I will provide in the description. The link you can download from this link. Thank you for watching my video.